What is that theorem? Okay, maybe I step. The theorem says that let T1, which takes U to V, and the T2, which takes V to W, be 1-to-1, linear transformations. One-to-one linear transformations. Then part A, the composition. In simple terms, what this theorem says is that if you have two linear transformations that are 1-to-1, for example, T1 is 1-to-1, T2 is 1-to-1, two linear transformations that are 1-to-1, then their composition, T2 composition composed with T1 is also 1-to-1, and similarly, also T2 composed with the T1, the inverse of this transformation is simply T1 inverse composed with the T2 inverse. Yeah. That's what the theorem emphasizes. That's what it emphasizes. I'm not going to prove it because just for appreciating. The next section.
Excuse me, sir.
Yes, you're excused.
Can't they ask for those theorems to be proved in exam?
A few of them that are important, like the one for the kernel. Yeah, they can be asked. That's a very good question, but not all of them. You just stick to those that are important. Now, the ones which I've just stated without proving, those are just for applying necessarily. But those that are proved, yeah, they are really essential.
Okay, thank you, sir.
Matrix. Of general linear transformation. Here, I think I should just compute an example. Otherwise, if I first build this construction will become a bit hectic. It will make you think that things are very difficult. To make you think that things are difficult. So what is the key issue here of exploration? Under matrix of general linear transformation, what are we interested in? Under this, previously we saw that we saw that every m by n matrix A, every m by n matrix A defines every m by n matrix A defines a linear transformation. Defines a linear transformation. Every m by n matrix A defines a linear transformation from Rn to Rm by matrix multiplication. What do I mean? Now, in the other example, which I have just computed here, recall that we're having T, I recall very well, T from R4 to R4. That's what we are having. That's what we are having. T from R4 to R4. And this transformation was the TAX, was defined by TAX equals AX, where A was a matrix, So that's why I'm saying that for that case, we are using a matrix. To define a linear transformation from R4 to R4. How? By matrix multiplication, where the matrix A multiplies with vector X. So previously, we have been interacting with that, where a matrix has been defining a linear transformation via matrix multiplication. Then in this section, we do the reverse. And what is the reverse? We do the reverse, i.e., in particular, this section we do the reverse. That is to say, i.e., how can we define a matrix? How can we define a matrix given a linear transformation? How can we define a matrix of a certain linear transformation? Yeah. Initially, a matrix was defining a linear transformation. So in this section, we explore how a matrix, how can we define a matrix of a certain linear transformation given that linear transformation? So there are some things here which are a bit I may not look at. Okay. Let me emphasize the things which I am going to use in my examples. Definition. What does this definition say? So let T taking V to W It's still taking V to W, B, a linear transformation. Let that be a linear transformation from an n-dimensional vector space. An n-dimensional vector space V into n-dimensional vector space into an m-dimensional vector space W. Suppose B and B prime are bases. Yesterday we defined a basis. So suppose B and B prime are bases for V and W respectively. So what does this mean? If B is a basis for V, if B is a basis for V, it implies that B generates V. Yeah, that's what I explained yesterday. I think we are using S as a basis, and that S was being spanned by that S was spanning V, if I recall very well. So B and B prime are bases for V and W respectively. Then the matrix representation of T with the respect to the bases B and the B prime denoted by is what is it? Is an M by N matrix A such that And this is the matrix that we are going to be establishing. Such that for every x in a V, like that. So we are going to be given a linear transformation. We are going to be given a linear transformation from n-dimension vector space V into m-dimension vector space W. Then if I have bases, yesterday I defined what a basis is. If I have bases V, I have a basis for V, something that generates V and something that generates W. Then the matrix representation of the transformation with respect to those bases denoted by that. So that is what the aim of this session is, to determine such a matrix. That is the aim. The aim here is to find such a matrix.
Excuse me, sir.
You're excused.
That A into matrix XB, is it not having translation? Is it not having a T symbol?
No, it's not.
Okay,
It's
thank
not.
you.
So the aim is to determine such a matrix. Such matrix. And we are going to see how to compute it. Such a matrix. By the way, technically, let me put this off. I capture it. Let me capture it as a remark. Remark. More formally, that matrix which you are seeing there, A, B, which is equal to Tx, B prime. More formally, we are going to see that in our example, but this is going to take on this form. T1 is a matrix which is going to be made by these columns. Tu2 B prime up to TUN B prime, like that. Those are going to be column vectors, and we are going to see how they can be determined. Then U1 where U1, U2 up to UN are basis vectors. Basis vectors. Then also, what else? If I look at an example. Now, if we have a linear operator, don't forget that a linear operator is a linear transformation from the same thing into the same thing. The image is equal to the domain. Also, there are some special cases for if V is equal to W, V is W, we have a linear operator which takes V to V. Yeah. If V is W, then it is usual to take B be the same as B prime when constructing a matrix, constructing the matrix for T. And in this case, resulting the resulting matrix is called the matrix representation. Or the matrix representation of T with respect matrix representation of T with respect to basis B. Basis B. The resulting matrix is called the matrix representation of T with respect to the basis B given by so it is formed by the following columns: TU1 B and TU2 B up to TUN B, where B is equal to U1, U2 up to UN. Now I take an example on how such a matrix can be computed.